All right, well, today we're going to simply look at the second hour exam review. Just something to wake you up. Um, Remember, there are still tutorial extra credits left that you can do. These will get you 10 points apiece. Only need to send the email once. Ones that work are Boyle's law, Charles, ideal gas law, basic pH, regular pH, and conjugate acid-base pairs. This will be the last opportunity that we have to do tutorials because the topics for the remaining of the course are not quite traditional chemistry. We're going to talk about earth science. We're going to talk about food, health, drugs, and whatever. So they're not really very much, don't lend themselves very well to tutorial type things. Remember, this has to be done before the day of the exam. Okay? So please don't disregard this. It's a lot of points. All right, let's go ahead and look at these questions. We have a gas in a sealed cylinder. Now we've seen our sealed cylinder with a movable plunger. Plunger is adjusted so the pressure increases, temperature remains the same. The volume of the gas will do what? What you should remember, of course, here's our sealed cylinder. There's our plunger. We have no weight or a small weight, no change in pressure, but something big on it, lots of pressure. We've increased the pressure and the volume has decreased. The way we say this is that the volume is inversely proportional to the pressure. That is the basis of Boyle's law. So going back to here, Boyle's law tells us that pressure and volume are inversely related. Increase in pressure leads to what change in volume? Well, that has to be a decrease. Any questions? Same cylinder. We're now going to warm it up so the temperature of the gas increases. Remember, whenever you're dealing with gas laws, the temperature that you must use is Kelvin, not centigrade or Fahrenheit, Kelvin. Centigrade plus 273 gives you Kelvin, okay? So just remember that. Okay, so if the temperature is going to increase, what happens with the volume? Well, this is Charles's law. And it tells us that temperature and volume are directly proportional. Okay, so they're directly related. An increase in temperature leads to what change in volume? Well, if it's a direct relationship, increase the temperature, we increase the volume. All right, now we're going to take our cylinder and we're going to pump in extra gas. Remember, when you're dealing with the gas laws and with gases in general, it doesn't matter what gas you have. They all behave exactly the same. Regardless of the molar mass or the identity of the gas or whatever, they all behave exactly the same. So we're going to pump more gas in. What happens to the volume? This is actually Avogadro's law. And Avogadro's law was stated in moles, but it said that the volume of a gas was directly proportional to the number of moles. Again, if it's directly proportional, we add more gas, we increase the moles, we increase the volume. Any questions? Very simple gas law concept questions. All right, now we have a bunch of equations. And the question very simply here is, which of these is Charles's law? Okay? Now we know that Charles's law tells us that volume and temperature are directly proportional. Right? Remember that. We know that. Charles's law, volume, temperature, directly proportional. Remember when we did this, we expressed that proportionality using the proportionality symbol. We read this as volume directly proportional to temperature, okay? What we did anytime we had the proportionality symbol was we replaced that with a constant and an equal sign. Proportionality can always be replaced by a constant and an equal sign. Therefore, if this is the relationship, and we're going to replace this with a constant and an equal sign, this works perfectly, doesn't it? This used to be the proportionality symbol. Now it's a constant and an equal. If you go through all of these, this one, if this was pressure, that would be Boyle's law, but that's not Charles. And none of these are equivalent to this guy. Any questions? All right, remember in lab, we did our flame tests, and that was fun. We took little bits of salt, we stuck them in the flame, and we got colors, and we could identify an unknown and stuff like that. A very, very simple form of emission spectroscopy. Well, the color arises because it's the actual color of the element. Atoms absorb energy. The metal atoms are reacting with the flame. The metal atoms are reacting with carbon dioxide. Well, we talked about this in lecture. Remember we said that because electrons surrounding a nucleus in an atom are quantized in various levels. Remember that each of these levels represents one of the periods in the periodic table. When this particular atom absorbs an energy, lots of energy, one of these electrons from a lower energy level can jump up to a high energy level. When it does, it's living up here on the outside. No, it's never been there before. Gee, this is exciting and stuff like that. But it's unstable out there. So once it's up at the top, it's going to fall back down. It's going to fall back down where it came from. But as it drops, it's going to give off this energy in terms of a light wave. Because this is a quantized drop, this is one particular wavelength of light. If the drop was bigger, it would be a larger wavelength. We looked at this using a little device, looked at an output here. If you were good, you could see the scale, and that's what you reported on your lab report, was the scale of the wavelength in nanometers. Remember that, wavelength in nanometers. Each of these corresponds to one transition in a given element. Okay? So this is where it comes from. So obviously, it's not the color of the element. It's not reacting with the flame or with CO2. It is simply this one. It absorbs energy, promotes electrons to higher quantum levels. When they return, they emit a discrete wavelength of light. Any questions? All right. When we did all this, we used this little thing to look at it. That's where we saw the scale in nanometers, and we reported those numbers and stuff like that. What was that called? Well, was it a stethoscope? No, that doesn't look right, does it? Was it a spectrometer? No, they never let us use anything that fancy, would they? Was it a spectrophotometer? That's even fancier. They never let you use that either. No, this was a spectroscope. Little blue thing, look in here, shine that at the light, and you see your diffraction grading up here. Any questions? All right, chapter 11. Here we were talking about radioactivity, specifically radioactive half-life. Now, radioactive half-life is a concept. Radioactive elements decay, and when they are half decayed, that's the time that it takes to do that is a constant for each element, and that will be its radioactive half-life. So our choices here. Half-life describes the time it takes from 50% of the initial mass to decay to form another element. B is basically the same sentence, but to form an isotope of the same element. Well, C was radioactive half-lives can be as long as billions of years. Well, we remember the little table. There are elements that have half-lives on the order of microseconds. And there are elements like uranium and plutonium that have literally billions of years for a half-life. So we know that C is correct. How about these two? Think about what happens when we have a decay. Let's just look at this guy. This is uranium-238. It's going to decay by losing an alpha particle. Alpha particle has 2 protons, 2 neutrons for a mass number of 4, same as a helium nucleus, but we form thorium. We form thorium because we lost these 2 protons, so the atomic number drops. Anytime you have a decay with an alpha particle or a beta particle, the number of neutrons is going to, protons is going to change. If the number of protons change, you must form a new element. All right, so that means that we're not forming a different isotope here. We are forming a new element. C is also correct. Therefore, A and C are correct. Any questions? All right, another lab experience. Lecture on it, we did it in lab, I even played with it here in the room with you. Which of the following solutions would be a strong electrolyte and conduct an electric current? Well, to remind you, this is the little device that you used. Stuck it in the liquid here. If you conducted electricity between the 2 little wires, the LEDs would glow. The brighter they glowed, whether both of them glowed or not, the stronger the electrolyte. So the more light, more electricity, stronger the electrolyte. So, which of these would be most likely to be a strong electrolyte? Solution of olive oil and water. Well, if you've ever made salad dressing, you know that olive oil doesn't even dissolve in water, does it? It just sits and it floats. So we can get rid of that. Solution of concentrated hydrochloric acid. Hydrochloric acid is a covalent compound, but water is able to break the covalent bond between the proton and the chlorine, form hydronium and chloride ions. The thing that makes something conduct electricity is ions. So B looks good. We actually did this one in lab. Sugar and water. Sugar is a polar compound. It does dissolve in water, but water is not strong enough to break the covalent bonds to make ions. Therefore, it does not form ions, and it will not conduct electricity. Only one on the list here that will is the concentrated HCl. Now, again, the thing to remember is anything that will form ions is going to be a strong electrolyte. Any questions? pH, we all love pH. We have a solution that's at pH 3. What does that mean? Solution is basic, it's acidic, it's neutral, it has 3 moles of acid or 3 moles of base. Remember, you can have your 3x5 card with your little whatever's written on it, and I would strongly suggest that you put the basic formulas that we're going to be using. For example, we remember that pH is simply the negative log of hydronium. That's the definition. We also know that if we want to find out the hydronium, all we have to do is take the antilog of this equation. So we get a new equation that's very useful. 10 to the minus pH is hydronium ion concentration. Now we can use this equation here. Our pH is 3, so if we substitute 3 in here, we have 10 to the minus 3. That's 0.001 moles per liter of acid. So this is 0.001 molar acid. Because it's lots of acid, because it's less than or greater than 10 to the minus 7, it is an acidic solution. Lots of acid, it's acidic. Any questions? The other thing to basically remember is, just on the scale, if your pH is less than 7, it's acidic. If it's greater than 7, it's basic. All right, here we're changing our pH from 7 to 5. What happens to our hydronium? Yeah, you had a question? About the pH? One of the basic things to remember is if your pH is less than 7, it's acidic. If it's over 7, it's basic. If it's exactly 7, it's neutral. All right, so here we're changing our pH. What happens to hydronium? Let's do this. It's going to increase by a factor of 2, decrease by a factor of 2, increase by 100, or decrease by 100. Well, we're changing 2 pH units, but remember this is a long scale. So let's show that by, again, looking at our basic equations. This is our basic definition. And like we did last time, 10 to the minus pH is hydronium. So we have 2 pHs, one at 7, one at 5. At 7, we have 10 to the minus 7 moles per liter of acid. At 5, we have 10 to the minus 5 moles per liter of acid. Obviously, This is a bigger number, isn't it? 10 to the minus 5 is bigger than 10 to the minus 7. By how much? By 100-fold. Therefore, our acidity, our hydronium ion, is increasing by 100. Any questions? Simply convert the pH values 7 and 5 to hydroniums. Simple to do. 10 to the minus 7, that's 7. 10 to the minus 5, that's this. How do they differ? We're increasing 100-fold as we go up. All right. The last lab that we did a bunch of little reactions and stuff and looked at stuff and whatever. And as one of the lab exercises, and what you did online, was to balance some equations. So there are going to be things from the lab that you can balance on this exam. Let's look at this, for example. Here we have sodium nitrate. If we warm up sodium nitrate, it can decompose to form sodium nitrite and oxygen. Now, just like in your lab book, this is an unbalanced equation. What you'll be asked to do on the exam is to take an equation from our lab, actually, and what you're going to do is insert coefficients. That's going to balance the thing. The only thing is that if we have a coefficient of 1, normally we would not show that, but on an exam you obviously can't just leave it blank, can you? Because then I don't know if you know it or you just didn't write it. So if it's 1, you must stick it in there. So let's think about how we're going to balance this. If you remember what we talked about when we were doing balancing, I suggested the odd-even business, okay? Here we have 3 oxygens on this side, odd number. Here we have a total of 4, even number. In order to balance, the first thing to do is to make them both even. We can make this even if we simply add 2 moles of this stuff. This gives us 2 times 3, 6 oxygens. So now our oxygens are all even, so that's good. Let's look and see what's happened on the other side of our equation. We now have 2 sodiums here, but only 1 on this side. Likewise, we have 2 nitrogens, only 1. Therefore, we want to stick a coefficient of 2 in here. That's going to balance our sodiums and our nitrogen. Now let's look at our oxygens. We know we have 6 on this side. We now have 4. 2 times 2 is 4. 5, 6. So we're balanced. But remember the 1. Stick the 1 in, just so I know that you know what you're doing. Now, the problem that you have is going to be one from our lab. So if you want to review those, you may. Otherwise, just think about the simple concepts. Any questions? All right, organic. Remember organic chemistry. I love organic chemistry. An organic compound that contains only sp3 hybridized carbon atoms is called what? Now this is a functional group, isn't it? The simple functional groups are useful because when you study organic, if you simply look at the functional group, that will tell you a generic reaction. You can basically ignore the rest of the molecule, just focus on the reaction of the group. So it's a very important concept. For things that only have carbon atoms, the functional groups that we looked at were alkanes, alkenes, and alkynes. If you will, single bonds, one double bond, and one triple bond. Now we constructed our single bonds here by taking one s and three p orbitals, combining them, and we called that sp3. Here we made our double bonds by taking one s and two of the p orbitals, sp2. And finally, for our triple bond, we just took one s and one p, made our skeleton. The p orbitals that are left over make the second and third bond. So alkenes, alkynes, and alkanes are our simple carbon functional groups. The question was, which of these contains only sp3? That would be the alkane. Here's an example of what we looked at. Again, this is a simple alkane. Every carbon is sp3 hybridized, and they're just stuck together in chains. Chains and rings and whatever else. Any questions? All right, we talked a little bit about basic biochemistry. Building blocks, one of the basic building blocks is called an amino acid. Called an amino acid because it has functional groups. It has the amino group and a carboxylic acid. So what we looked at was something like this. These are two sample amino acids. Once again, they have the amine functionality, and they have the carboxylic acid. This also has a side chain like this. This one has a side chain that's just a methyl group. But again, the amino group and the acid group. Now, we said that we could take the amino group of one and the acid group of another, and we could link these together. When we do that, we're going to lose water, and we're going to form another functional group. And that's called an amide. It's also called a peptide bond if you happen to be a biologist. We formed an amide, a new functional group. And this is how we link amino acids together. If we link a bunch of them together, here we have leucine, glycine, serine, and alanine. When amino acids are linked together in short chains, they're called peptides. Now, if we take this process and keep going, we can wind up with very, very long chains. This is called a protein. Long chains, again, with our peptide bonds from our amino acids, form our proteins. Let's look at DNA. Remember, DNA has a sugar phosphate backbone on both sides here, and it has DNA or RNA bases they're referred to. Adenine, thymine, guanine, cytosine, and these hydrogen bond with each other. As far as this question is concerned, however, if you look at this structure, there are no amino acids here, are there? So, going back to our question, They contain an amino group and a carboxylic acid. They can polymerize to form peptides, and they are the basic building blocks of proteins. However, they do not exist in RNA or DNA. All right, I told you want to make sure you know all the very simple relationships, especially for the pH and maybe for the gas laws. Those are your big equation guys. There's one very, very important equation that relates pH and pOH. It's valid in any solution as long as you're at room temperature, 25 degrees. What is that relationship? pH plus pOH is always equal to 14. If you have a neutral solution, pH is 7, pOH is 7, it's 14. If you had an acidic solution with a pH of 5, the pOH would be 9. So it's a very, very simple equation. Even I can remember it. Any questions?
Anyone?
Any pH, right? Any pH or pOH, you can calculate the other. It's always equal to 14. All right, which of these describes a basic solution? We already said this, and of course you all wrote it down and you remember it. If the pH is less than 7, it's acidic. If it's greater than 7, it's basic. All right, we're looking for a basic solution, right? So for A, our pH is less than 7. This guy is going to be acidic. So it's not A. Now you know that neat equation we just talked about? That I said pH plus pOH was always equal to 14, right? Well, that comes from the fact that concentration of hydroxide times hydronium is always equal to 10 to the minus 14. But less than or equal to, I'm sorry, that's nonsense. And finally, for C here, if hydroxide is greater than hydronium, well, hydroxide is the thing that makes solutions basic, isn't it? If you have more hydroxide than hydronium, by gosh, it's basic. Any questions? All right, we have a very simple acid-base reaction here. We're interested in the forward reaction. Now remember, this is what we call an equilibrium. Equilibrium, the reaction can go both forward and reverse at the same time. So they're going boom, 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 boom. Okay? That's what an equilibrium is. But here, we're only interested in the forward direction. Now, what we're looking for here is the conjugate acid-base pair in the forward direction. So what we want to do is look at our acids here and our bases and see what's going to fit. What you want to remember, just like pOH, pH, equal 14. Remember, an acid loses its proton to form its conjugate base. Right? Acid loses its proton to form a conjugate base. Now, what we have to do is simply look at these guys and see if the first guy and the second guy differ by one proton. Right? That's the first test you want to do. Here we have hydrogen sulfate and sulfate. Yes, they differ by one proton, don't they? Sulfate and hydrogen sulfate, this is going the wrong way. Here we're gaining a proton. Dihydrogen carbonate and sulfate? Well, they're not even the same groups, are they? Dihydrogen carbonate and hydrogen carbonate. Yeah, here we've lost one proton. And finally, dihydrogen carbonate and hydrogen sulfate, not even the same compound. So we're dealing here, our answer is going to be either A or D, right? Because both of these lost a proton to form this. So what we need to do is simply look at our reaction here. In our forward direction, which of these guys is donating the proton? Hydrogen sulfate loses its proton in the forward direction to form sulfate. This is the acid and its conjugate base. Dihydrogen carbonate loses its proton in the reverse direction. But in the forward direction, hydrogen sulfate and sulfate. Any questions? Differ by a proton. That's what you need to remember. Yeah?
So D would have been the reverse one?
Yeah, that
Okay.
would be the reverse one. All right, in order to calculate an unknown parameter such as pressure, temperature, whatever, in a single state gas law problem. When we talked about gas law problems, we said that there were two basic categories. Single state, that's where you know this, this, and this, and you're trying to figure out what that is. Or two state, where you have something, make a change, and you have something else. What we say is, in a single state, you want to use the equation PV equals nRT. Okay? So as soon as you read this, single state, in your mind, the little rhyme should go off, PV equals nRT. So right away we know that C is going to be a correct answer. P1, V2, P2, V1, this isn't even boil. That's wrong. Just ignore that one. But is it possibly A and C? What you want to do is look at A and see is it the same as C. If in fact we multiply by RT, we would get RTN equals PV. That's this, just backwards. Those two are the same equation, aren't they? So A and C are both correct. Okay, which again, this is conjugate acid-base pair, which are correct regarding the acid-base pair. Base will have one less proton, one less positive charge. Acid will have one more proton, one less positive charge. Conjugate base is formed by reaction with hydronium. No. Acid is formed with hydroxide. No. So let's look at these guys. Remember what we just said, an acid will lose a proton to form its conjugate base. We know that, we just said it. The acid loses its proton. Now what's the charge of a proton? +1. So if it's going to lose that, it's going to lose its +1 too, right? Conjugate base will have one less proton and one less positive charge. The acid loses its proton and it also loses its positive charge. Now comes the question that everybody's going to hate on the exam. But get yourself geared up because you can do this. Here we have a solution with a pH of 12.26. Calculate POH, hydronium, and hydroxide ion concentrations. For this, please make sure you bring your calculator with you because you will have to do logarithms and whatever in order to solve this problem. All right, let's get over our panic. We know a pH. How can we calculate hydronium? We know that hydronium is simply going to be 10 to the minus pH. If we have trouble remembering that, we wrote it down on our card. All right, so let's plug in. Where we have minus pH, let's plug in minus 12.26. Now what you have to do is pick up your friendly calculator. You're looking for 10 to the x. You type in minus 12.26, hit 10 to the x, and you should get 5.5 times 10 to the minus 13. All right, the next thing let's do is POH. This is so simple, isn't it? Why? Because as we all remember now, pH plus POH is always equal to 14. And we know what pH is. Therefore, this is just simple subtraction. 14 minus 12.26, 1.74. And finally, we have to somehow get hydroxide ion concentration. Two simple ways you could do this. Probably the simplest is just the same operation we did here for hydronium. Remember, hydroxide, just like this guy, concentration is 10 to the minus POH. So the same bit of math that you did here, you're doing here. We substitute for the POH that we just calculated, 1.74. Take our calculator, we type in minus 1.74, hit 10 to the x, and you should get 1.8 times 10 to the minus 2. Any questions? All right, the last question on the sample exam here. Which of the following is correct regarding subatomic particles in common radioactive decay? Alpha particle consists of 2 protons, 2 neutrons, no electrons. Beta particle has a mass of -1. Gamma particle, very high energy. Electron with a charge of -1. Positron is a positive proton. Or they're all right. So remember what we said about simple radioactive decay. There were 3 particles that we wanted to look at: alpha, beta, and gamma. Alpha particle, we said, had 2 protons and 2 neutrons. Because of that, it has a charge of +2. Beta particle is an electron, just an electron that escapes the nucleus. When that does that, it has a charge of -1 because it's an electron. And finally, a gamma particle. Gamma particle is just a photon. It's super, super high energy light. And because it's high energy light, it's neutral. It has no charge. So this is what we said. We all remember this: alpha, beta, and gamma. Alpha particle consists of 2 protons, 2 neutrons, and no electrons. That's just what we just said, right? That's an alpha particle. Beta particle has a mass of -1? No. No, it's an electron. It has a teeny, teeny, tiny mass, but it certainly isn't -1. Gamma particle is a very high energy electron. No, it's not an electron. It's a photon. It's a ray of light. And anyway, its charge is certainly not -1. And last, a positron is a positive proton. Well, a proton's positive, isn't it? If you had a positive proton, you would just call it a proton. A positron is a positive electron. All right, so the only one of these that's correct is this guy. Any question? Yeah,
Can you go back to the previous breakdown for number 19?
number 19. Sure, I think. There we go. For number 19, what we did was simply solve for hydronium. It's 10 to the minus pH. We remember that pH in POH was always 14. And here we have 10 to the minus POH to give us hydroxide. So the same concept here, just an OH instead of the H. All right, remember, exam is next Wednesday. Make sure you bring your calculator. You may have a 3x5 card as well.